Today we're going to be talking about scaling Kubernetes networking beyond 100,000 endpoints. My name is Rob, and I'm going to be joined with Minhan, also my coworker from Google. Today's talk is going to be divided into 6 different sections. We've got a problem statement, which will kind of give some background into why we did all this work. Then an EndpointSlice API introduction, just a very high-level idea of why we designed the EndpointSlice API and what it can accomplish. And then I'll talk about how it works, some of the key functionality involved. And then I'll dig a bit deeper into how we could profile Kubernetes to dramatically improve the performance of these implementations. And finally, putting it all together, talk about how that translates into performance at and even beyond 100,000 endpoints. And in conclusion, I'll talk about what's next, what's coming up that is going to be based on this functionality. And there's some really exciting stuff. But with that, I'll hand it over to Minhan to give some background.
All right, thank you, Rob, for the intro. So before we go to our solution, so let's understand what the exact pain points our users have. So there are mainly 2 pain points when using Kubernetes service at scale. The first one is that there's currently a limit for number of endpoints within a single service. So this is around 5,000 endpoints in a single service. So the second one is that the user may observe a significant performance degradation in a very large cluster. To be more specific, an endpoint update of a large service containing 5,000 endpoints in 5,000 node cluster may freeze the control plane for a couple of seconds. So both of these questions, these problems are originating in the same thing, which is the Endpoints API. The API was designed in the very early days of Kubernetes, and the scalability wasn't an important area of consideration at those days. So in short, the problem lies in the fact that the endpoints object contains a full list of all endpoints behind a given service. So that is the subset section of the endpoints API object. So what's wrong with that, right? Let's walk through rough estimation. So let's say there are P number of backend pod because the endpoint object needs to contain a full list of endpoints behind the service. Then the size of the endpoint object is proportional to the number of backend pod, which is OP. So 1.5 megabyte of endpoint object can roughly contain 5,000 endpoints inside a service. And that there's a various aspects that can influence the size of the endpoint object, like the length of the name and the namespaces of those backend pod. Is it the IPv6 endpoint or the IPv4 endpoint? So what happened when we go beyond 1.5 megabyte? So first of all, there's a limitation in the SCD for the maximum size of an endpoint, of an object, right? And the default value is set to 1.5 megabytes. Although this value is configurable, the performance characteristics of SCD are started to getting worse. So we don't want to do that. So to summarize, the limitation of the number of endpoints inside a single cluster is actually the consequence of the SCD size limit. So let's take a look at the second aspect of the problem. That is the performance degradation. So in order to understand that, we need to do a quick recap on how does the service control actually works within the Kubernetes behind the scene. So when the service gets created, the endpoints object gets created. So the pod gets created, then pod gets scheduled, the kubelet watches the pods running on itself, and then kubeless signals the container runtime to basically implement this container and this pod, and the container runtime says it's running and healthy, then the kubelet updates the pod status to be ready. And the endpoint's controller watches the pod, and then it updates the endpoints correspondingly. And kubeproxy pick it up and program iptables, IPVS, and to implement Kubernetes services. And then eventually the endpoint is programmed. So what happened is that each kubeproxy running on each node needs to watch all endpoints of the whole Kubernetes cluster, right? So this is because it has this information is necessary for it to basically implement Kubernetes service on each node. And that translates to there are n number of nodes means n number of watchers, right? And because there's no magic in sending update through the network, so n number of copies, object copies will need to be sent from the API server to each watcher. And combined with the number of backend pod and the size of the endpoint object, which is proportional then to the number of backend pod, and times the number of watcher, so the total bytes transmitted per update is O(n) times P. So let's give some real numbers here. So the number of nodes, let's say it's a large cluster with 5,000 nodes, and the size of the endpoint object is 1 megabyte, which contains, let's say, 5,000 endpoints. Then in each update, we need to send 5 gigabytes of data. That is basically the size of a full DVD, right? So for one endpoint update for a large service. And let's do a further estimation, right? Let's say total bytes transmitted per update is 5 gigabytes. And what about we do a rolling update? Let's do a rollout to this large service. And this service, let's say, have 5,000 endpoints. And that roughly translates to more than 5,000, maybe more or maybe less, depending on what's your rolling update strategy. Then let's assume it's 5,000 updates, right? Then that translates to 25 terabyte of data. That is a lot of data. In the contrary, what user expects is that it wants to run large services in large clusters, and it wants to be agile as well, right? It wants to enable auto-scaling, it wants to roll out frequently, and that translates to high churn within the service. And all of this should just work, and Kubernetes should provide this kind of capability. So we look at this problem space, and at first we consider a few tactical solutions for this problem, and we later realize those tactical solutions may contain other downsides. So we decided to reinvent the Endpoint API altogether. Now we are trying to, let me quickly walk through what is EndpointSlices API. So the goal of the Endpoint API, the primary goal is to address the scalability constraints that we listed out in the previous section. That is to support tens of thousands of backend endpoint in a cluster with thousands of nodes. Since we're basically reinventing and redesigning the whole endpoint, the Endpoint API, we throw in a bunch of other extension points, which we wanted to address dual stack and topological aware services and things like that. So we're gonna talk about this a little bit later. But first we focus on the first one, which is the scalability aspect of this. So at a high level, we want to slice a monolithic big endpoint object into multiple objects. And each object is called EndpointSlice. So this is very similar to database sharding, but it comes with some Kubernetes-specific flavors. So kubeproxy watches all endpoint slices, which represent all endpoints behind services. And when the endpoint update happens, only the corresponding endpoint slice gets shipped to all kubeproxy, and the rest doesn't need to be shipped and transmitted. So with all that, this is a very high-level intro to the EndpointSlice API, and I will let Rob to talk more about how it actually works behind the scene.
Thanks, Minhan. Yeah, that's a great background for the EndpointSlice API. And I'm just going to provide just a little bit more detail on how it actually works, the different pieces that come together to make this work. So there's three core components that I want to talk about. There's an endpoint slice controller that watches services and pods and creates or updates endpoint slices. This is very similar to the endpoints controller. It's just managing endpoint slices instead. Then we have a newer controller called the endpoint slice mirroring controller that watches custom endpoints and mirrors them over to endpoint slices. And finally, we have kubeproxy. This is not a new component, but we've added new functionality here. So instead of watching endpoints, it can watch endpoint slices and update iptables or IPVS proxy rules. I wanted to cover just a little bit more about the endpoint slice controller though. The endpoint slice controller had a couple key goals, and some of it is not always intuitive. So we wanted to reduce endpoint slice churn. This lines up with what Minhan was saying earlier. Every node is going to be watching endpoint slices, so updates are very expensive. We want to minimize the number of endpoint slices we're updating because every single time we update it, it has to get sent out to every node. Then we want to limit the requests per second to API server. Endpoint slices that are too small will result in too many resources being updated. And on the other hand, if we have endpoint slices that are way too big, it will result in a DVD's worth of data getting sent across the cluster, even for the tiniest of changes. And we'll be right back to the problem we had to begin with. So with that background, I wanted to explain one relatively unintuitive part of how this controller works. So let's imagine an example where you have two endpoint slices. Now keep in mind that endpoint slices by default can hold up to 100 endpoints. So we have one endpoint slice with 70 endpoints and one endpoint slice with 80 endpoints. And we have 50 endpoints to add. Now you would think, well, this is a really straightforward update. You can just update those two endpoint slices and everything will work fine. But instead, what the controller is going to do is create an entirely new endpoint slice because we prefer a single create over multiple updates. There's a lot of extra detail and logic here that means that this rarely actually happens. Often in an individual sync, we're also updating endpoint slices, and if we are, we fill them up as much as we can. But if we're not updating anything, we prefer to create something new as opposed to run multiple updates. So let's talk about how this actually translated into performance. This API and this functionality was alpha in Kubernetes 1.16. And it worked. That was the good news. But when we actually started to look at performance, things were just slower. Kubeproxy was very noticeably slower when using endpoint slices compared to endpoints. And part of this made sense. The implementation was more complex. There was more to do. And that was almost fine. But endpoint slice implementations really should have been faster because we really wanted to scale this out. So I did some profiling with a really cool tool called pprof against kubeproxy just to see if there were any bottlenecks that we could get rid of. So if you've run pprof before, you're probably familiar with something that looks a bit like this. This is the result of running a pprof report on kubeproxy specifically for CPU time. It can profile any number of components, but in this case, I was interested in CPU time. And with that background, I found three really important ways we could improve performance here. First, we had endpoint.ip function, which was taking 43% of total CPU time. That's an absolutely massive amount for doing something that shouldn't have taken any time. I had thought that this function was just getting a string. That's it. But what it was actually doing was it was calling net parse IP to parse an IP out of a string port IP port combination. There's no reason we couldn't have just used the IP port string here. So making that really simple change ended up really improving performance here. The second big performance update was we had a function called handle update endpoint slice that was using 55% of CPU time. And I should mention, just to be clear, that this was 55% of CPU time after we fixed the previous issue. We were calculating this new merged data structure every single time we got an endpoint to update to an endpoint slice. The problem was we weren't actually using that until we ran iptables updates or IPVS updates, which was a lot less frequently, at least when there were frequent updates. So changing this logic to only run when we needed it ended up making another very significant difference. And finally, there was this function called detect stale connections, which after the previous two fixes was using 88% of CPU time. It was entirely necessary to clean up stale UDP connections, and it was pretty hard to optimize. But one thing we'd missed is it was running for every connection, and it only needed to run for UDP connections. So we restructured this, and that got rid of some very significant CPU time. So if you look at what that resulted in, the big, tall, long yellow line there represents my initial endpoint slice implementation. And this is scaling from 0 to 10,000 endpoints in a cluster. And you can see that my endpoint slice implementation was very slow and took 3 minutes longer to complete, in addition to using more CPU for the entirety of its running time. On the other hand, all the other implementations finished on time, finished right as the scale-up happened, and they were reasonably efficient. But you can notice that the initial endpoints implementation was also not great. The bottom two lines that are relatively flat are these improved and optimized implementations. And you can see some significant improvements there. But I know it's hard to understand real numbers from a chart. So to take a look at real numbers, here's what we observed. The endpoint slice implementation was around 20 times faster than the baseline endpoints implementation in 1.16, and even still more than 3 times faster than the updated and improved endpoints implementation in 1.17. So very significant improvements just from some basic profiling. But if you're at this talk, you're probably not just interested in 10,000 endpoints because, well, we know that this works at 10,000 endpoints and it's pretty reliable at this point. But we really want to understand, well, just how far can we push this thing? So let's talk about 100,000 endpoints. But before we get too far into this, I have to provide some caveats. These results are absolutely not scientific. This is just what happens when we wanted to know what would happen at this scale. This is by no means an endorsement of running a service with 100,000 endpoints, at least not in production. And I did absolutely nothing to tune this cluster for better performance at scale. It was running with all the standard E2E test settings. So if anything, it probably was tuned against scale. There's some things like really verbose log levels which have to have some kind of negative impact on performance. So with appropriate efforts to tune these components, I'd imagine results could have been better. So let's talk just briefly about how I set this up. So I used kubetest with most defaults used for E2E test clusters, and I ran this on a 1.19 alpha pre-release. So this is after code freeze, but before 1.19.0. So somewhere in that mix, I have a specific commit there if you're interested, is what this was run against, and you can see the command I used to spin up this cluster. The end result was 4,002 nodes. One of those was the master. One of those was for Heapster, and there were 4,000 nodes for everything else. I should point out these nodes were relatively small. They're N1 standard at 1, so only one core of a CPU. So keep that in mind when you look at the numbers later on. Well, we really did put a lot of pods on these nodes, and that also could have adversely affected performance. So I learned pretty quickly on that although a 100,000 pod deployment does work, it, at least in my case, was impossible to actually get any information about it, because if, as an example, you try to run kubectl get pods, and at least in my experience, it would consistently time out. And because every pod inside a deployment shares the same set of labels, it was very difficult to just get an individual pod or a small subset of pods. So instead, what I ended up doing is 10 deployments with 10,000 pods each. And surprisingly enough, there weren't any issues listing 10,000 pods at a time. And I targeted all those pods, all 100,000 pods, with a single node port service. It was a node port service, but all my testing, all my load testing was based on the cluster IP from within the cluster. But it did technically have node port functionality as well. Now, as you'd imagine, as we're scaling up, endpoints hit that etcd object size limit at around 10,000 pods. And this is what Minhan mentioned earlier. There's a limit to the size of an object in etcd. And you can configure that to a point, but increasing that too much is just not going to help very much. So you can see that we hit just over 10,000 endpoints and then just consistently got errors whenever the endpoints controller tried to update endpoints from that point on. But EndpointSlices kept on working as expected. And so we ended up with 1,006 EndpointSlices to store 100,000 endpoints. And I have to mention this is, again, by design, because the controller is minimizing updates, and it's always going to create a new endpoint slice instead of updating multiple endpoint slices if those are the two options. So not every endpoint slice was completely full, but reasonably good distribution here. Now you have to wonder, at this kind of scale, how crazy does iptables look? And well, the answer is pretty crazy. 400,000 total lines, and over 100,000 of those lines were probabilities. Now, if you're familiar with how kubeproxy's iptables implementation works, it is really just decreasing probabilities. So the very first item in this list would have a 1 in 100,000 chance of going to that endpoint. And if that isn't picked, it goes one further down the list, and there's a 1 in 99,999 chance that it will go to that endpoint, and all the way down the list. So just a really, really long chain of probabilities. It sounds really strange, but it ends up being fairly reliable and fairly performant. But at this point, once we got into 100,000 probabilities of 100,000 endpoints, kubeproxy updates were really slowing down. So sync proxy rules, the actual code and logic behind kubeproxy, well, I sent 50,000 requests across the cluster to this service, and they averaged a 883 millisecond response time. So not exactly blazing fast, but it did work. And I specifically used Minhan's fork of Hey because it includes this really cool functionality that allows you to see response distribution. And used appropriately, you can see exactly how many different endpoints, unique endpoints, responded to your requests. And so in this case, my 50,000 requests were distributed across 12,700 pods. Now, I also had to test out IPVS because I was curious just how that performance might differ. So there's a different proxier mode in kubeproxy for IPVS, and just enabling that, it worked reasonably well. Okay, so let's talk about IP tables. We had a 50,000 requests sent across the cluster to that service. We had an 883 millisecond response time on average, and the requests were distributed to 12,700 pods. And the way I was able to determine that was with Minhan's fork of Hey, which made it very straightforward to see just how many pods we were able to reach with these requests. So 12,700 unique pods. So this is not exactly blazing fast, but it did work. And then for IPVS, I had to try out the IPVS proxier mode. And for that, we sent another 50,000 requests, again with the same library. And the average response time was a bit slower, but the requests were more distributed, going to 17,000 pods. So again, continued to work, but a bit slower with IPVS in this specific instance. But of course, you're probably curious. I know I said more than 100,000, beyond 100,000 endpoints. So this all continues to work well with 120,000 pods. So in this case, we have 1,204 total endpoint slices that we ended up with, and it all generally worked. But it's at this point that I have to provide a few caveats, because as much as this worked, it wasn't always pretty. There were errors, and I would be remiss not to mention them. So first, it's worth mentioning that the API server would time out. This is one example of it timing out on an endpoint slice watch. But there are other examples too, where it would time out and eventually connection would be reestablished and things would work. But these errors became more common the further I pushed the limits. So the closer I got to 120,000, the more frequently I'd observe errors like this. Then there's kind of a trickier error around endpoint slice updates. The way Kubernetes controllers work is they use this shared cache of resources. This dramatically decreases load on API server, but it does mean that sometimes a controller may be operating on resources that are not completely up to date. And if, for example, say the endpoint slice controller chooses to try to update a resource that it has a stale copy of, you'll get this kind of error message. The object has been modified. Please apply your changes and try again. So that makes sense, but it is something that will appear more and more in log messages. And we're working on ways that we can try to work around this, but unfortunately with caching, I don't think we'll ever be able to completely get rid of the possibility this could happen. And as you would imagine, the more and more endpoint slices you get for a service, the higher the likelihood of these events happening is. And then finally, as I'd already mentioned, the endpoints controller just kept on running into that etcd object size limit. We're hoping to truncate endpoints in the future so that when you get to this large scale, the controller stops trying at a certain point, but right now it'll just keep on trying and failing, and that's just unfortunately what the story is at this scale right now. So let's look at some real data. This is the results I got over those few runs with 100,000, 120,000 endpoints for both IPVS and IP tables. I should say these results are definitely not scientific. They represent just a few runs from a single node in a cluster that's running pre-release software. Any number of factors could influence these. So with that said, I want to highlight a couple things. IPVS update times were dramatically faster, 5 seconds instead of 25 or 29 seconds with IP tables. And you can also see the IP tables performance hit as you gradually increase the number of endpoints, becomes more and more significant at scale, whereas IPVS performance is relatively flat regardless of scale. So that's great. It works. It works well, reasonably well at high scale. But what's next? Let's talk about the really cool features that endpoint slices are going to enable. We have some really exciting goals for Kubernetes 1.20. I realize there's a chance not all of these are going to make it in to Kubernetes 1.20, but at this point, we're hopeful. So we're trying to work towards a plan for automatic topology-aware routing and endpoint slice subsetting. These two features are really closely tied together, and they're very related to everything we've discussed so far. So I'm going to follow up on those in a couple additional slides. But beyond that, we also have some really exciting work to support multi-cluster services and significant dual stack updates, both of which are going to be heavily reliant on endpoint slices. And if you're interested in using endpoint slices on Windows, we're hoping to have beta support for kubeproxy in Kubernetes 1.20. But let's talk a little bit more about that automatic topology-aware routing. The concept is really simple. Right now, if you make a request anywhere inside a cluster to a service, you're equally likely to end up at any endpoint anywhere else inside the cluster. So it doesn't matter if it's the same zone or a different zone, equally likely. The idea is, why not try to keep zones as requests as close to their origination as possible? So endpoint slices already store that topology information for each endpoint, and kubeproxy can be updated to prefer endpoints that are in the same zone or region. And as you can imagine, this has potential for much faster routing and significant cost savings. Now, if you take this idea and add this next idea, you have significant ability to save costs and decrease API server load. With subsetting, the idea is, what if, not just topology-aware routing, but what if kubeproxy could just select the endpoint slices that were relevant to it? So the ones that represent the closest endpoints to it. And if we can restructure endpoint slices a bit, I think this will be possible. And this could result in very significant performance improvements and significantly less load on API server and kubeproxy. Even if you don't want to run 100,000 endpoint, these performance improvements are going to be noticeable at all levels. The upper limits of service size are dramatically higher now, so that's something to be excited about if you've been thinking about running larger services. And I have to be honest, endpoint slices don't and can't solve all the bottlenecks, but they have solved a really significant one. So new features like topology-aware routing and subsetting will result in really significant scalability improvements, and I'm very excited about the future with endpoint slices and all the great functionality we're going to build on top of this. Thanks so much for your time. I've enjoyed it. Feel free to reach out to me or Minhan if you have any questions. Thanks.
Hey, thanks for being part of our talk. We have time to answer a couple questions that came in. Thanks for all the questions. Again, I think you'll see in chat, we're also going to be on the Kubernetes networking channel in CNCF Slack if you have additional follow-up questions that we can't get to here. One question that came in relatively early in the talk is, do you think going beyond 1 million endpoints is going to be possible in the future or even the near future? And I think that's a great question. What we can say is the Endpoints API is no longer the bottleneck. With EndpointSlices, we've solved one of the bottlenecks here, but as this talk kind of covered, there are other bottlenecks that we'll run into. As an example, current implementations of kubeproxy were really not intended to reach the scale of 1 million endpoints. And also there's some some other load, say API server that may need some addressing. So those are some high level things that I know we need to address if we really wanted to support 1 million endpoints. I know if there's sufficient demand, the open source community is awesome and always working to improve the scalability of Kubernetes. So maybe. Minhan, I don't know, do you want to take on one more question?
I think we're at time, and then I have already
Okay.
typed in a bunch of answers to the questions.
Okay.
Oh, there's one more. Oh, there's a lot more coming in. Okay. So, okay, let me pick the first one. I want to run 10k NGX web server pods for same application. What should be preferred idea? The first A is one cluster and run all 10k pods in same namespace on physical server. B, split using namespace with 1k per namespace. C, distribute 1k on 10 clusters. I need speed. So I would. It really depends on how your deployment model. Like we take these a lot of questions similar to this before. So basically, why do you need to run like 1 million endpoints behind a service in the first place, right? Why can't you chop it up? So, like for instance, one aspect to consider is like how to deploy. Do you have a load balancer or some multi-cluster service implementation that can target backends across different clusters, right? And then how do deploy, how do rolling update through those like different deployments in different clusters. So like more clusters definitely give you more availability and high, like basically reliability built in. But it takes like basically it's more painful to roll out and then debug. And you can have, I would say it really depends on your use case. And then there's a balance between basically the number of shard of your deployment and the number of your clusters. Yeah, so the answer is probably it depends based on your requirements of your reliability and how agile you want. And then there are also some other bottlenecks on the deployment controller itself that it can't support, let's say, 1 million pods behind the deployment. If you scale a deployment to 1 million pods, it will basically keep on creating pods in the loop and take a while to actually realize those 1 million pods. So yep. So sorry, we are at time. So I will try to type in some of the answers to the questions.
Yeah, and I'm also seeing some questions come in on Slack, and we'll follow up there as well. So thanks so much for the time.
Thank you.